Hi, and welcome back to episode 2 of the series from 8590 on programming for FRC. So, today we are going to be looking at sensors, and sensors is pretty much all about making people do less work, right? A lot of what makes a good team is having an automated robot. And so every time your driver is not thinking about doing a manual task, they are thinking more about the game. And as programmers, it's our job to help assist with that. So right here, I have the 4 main types of sensors that we use. And there are more, but this is going to serve as mainly a blueprint on how to use these. Again, all code is available on github.com/frc8590. So you should be able to just come in here and take what you need. But keep in mind, libraries get updated. Right before I started this recording, I had to reinstall libraries because they were updated. So make sure you do that. But without further ado, we're now going to cover each of these and talk about how we use them and why we use them. So the first that you will see is an analog input photoelectric sensor. So a photoelectric sensor is something that detects the amount of light that is by the sensor. And this is very good for object detection because we can slap a sensor onto a part of our robot and say we want to check when a ball has entered the robot so we know to start shooting it out. In this case, you just wait until there is very little light because the ball would be blocking the sensor from receiving light. We'll get more on actually reading that later, but what I want you to focus on right now is that the type is an analog input, right? And so this means, this is honestly better for electrical, but as programming, you're going to be doing a lot of electrical because sometimes electrical is not there for every little thing you need. So you should know analog input is plugged into the analog ports of the RoboRio. And we'll do a bit more on photoelectric sensors as we go on, but I want to cover the very basics of each of these first. The next we have is the laser can. This is our current distance sensor that we use, and if you know anything about FRC wiring, you might be able to guess that this is plugged into the CAN bus, right? And it's very simple. You will see on it they have CAN ports. You attach those to the CAN bus, and you will be able to start reading out distance. Distance is useful for all sorts of things, but to give a recent example, we wanted a very accurate way of measuring where our elevator was in 2025, and the way we did that was through, one, having an encoder, but two, having a distance sensor so we could always be measuring exactly how high up the elevator is. The next is a limit switch. If you're unfamiliar with what a limit switch is, it is a very basic kind of switch, as you can expect, but it also is made to detect when something is in contact with something else. In that, let's say I have a robot and it's driving and I want to detect when it bumps into the wall, right? And let's just say, for the sake of this, I have no vision and the robot has no vision and there's no way of telling. What you can do is have sort of like a button on the outside of your robot, and you just wait until you drive into the wall and that button gets pressed, and that's exactly what a limit switch is. There are different types. Some are magnetic, some are big mechanical ones, but what's important to know right now is that they are digital inputs, and so that means you're plugging it into a DO pin on your RoboRio, DO standing for digital input output. Lastly, we have the encoder. The encoder is a very important part of FRC because it's how we keep track of our motors. And we'll see more of that in odometry and things like that, but I'm kind of getting ahead of myself. What's important is that when we are supplying, as we saw in the last video, 50% power to a motor or 100% or 25%, we have no idea what kind of distance that actually does, right? We're kind of just spitting power into it. And so it's very important to be able to keep track of those things. We'll see that later when we talk about PID. But for now, all you need to know is that this is tracking rotations, right? And this is also going to be a digital input output though it's not called a digital input output, that is what it is plugged into. And we'll cover now how to take in all of these and extract information from them. And I'm going to skip over this segment for here. I'll wait till we talk more about encoders. So first is the photoelectric sensor. It's very simple, partially because it's, an analog sensor. All we want to do is decide what is the correct amount of voltage, right? Because, as we said, it detects light, right? So if there's a lot of light, say, then it might get 5 volts, right? And if it's a vacuum of space and there's no light around, then you might have 0 volts, right? And so you just have to figure out what is the correct amount, right? And so a good way to do this is constantly print the voltage, right? You can run a loop just saying, print photoelectric sensor dot get voltage. You can see what is the voltage when the object is not there, and then you can put the object there and see what does the voltage change to, right? And then you can do something like this, right? So in our case, we could see in a recent year when the object was there, it was about 4 volts. When the object was not there, it was 4 volts. When the object was there, it was roughly 2 volts. And so we say, all right, we can put a nice middle ground, right? If it is less than 3 volts, then we can expect that the object is there. Moving on, we have the LaserCan distance sensor, right? So this might look a little bit confusing, but don't worry, it is mostly just checking for errors. And I'm going to go through it line by line so you can understand. First, we have LaserCan dot measurement, and that is going to be the class, right? It's its own special type because Grapple Robotics likes to do their own things. And we're going to call it measurement, and it's going to equal our LaserCan's get measurement retrieval, right? And that is going to be a sort of class that contains a lot of different things in that there are certain measurements within it, and I'm kind of getting ahead of myself. You'll see it in the coming lines. I first want to get this if statement out of your mind. You don't really need to worry about it. It's just checking for errors, right? So you can see we're checking that the measurement is not null. That's one possible error. And we're checking that it's a valid measurement. And if it is both of those, then good job on us. We have a working distance sensor and we can continue on. Otherwise, we return -1, as you often do in computer science when there is an error. And it works here because there is no way in which an object would go through your distance sensor and you'd still be able to measure it. But what you will see here, if everything is right, is you return measurement dot distance in millimeters, right? That's how you can retrieve the distance, except in our case, we want it in meters. So we're just going to say measurement dot distance millimeters, and we're going to divide it by 1,000 because there's 1,000 millimeters in 1 meter. And then, of course, we might not always want the exact distance from the distance sensor. Maybe we want to have something else be decided as 0, right? Let's say we have an elevator that's going up and down, right? And we want to control the 0th floor, right? That very bottom level. We want level 0 to not be as close to the distance sensor as possible because often the distance sensor is actually below where the elevator can be. And so that's going to be an offset, right, of what the sensor believes is 0 and what we want to think of as 0. And that's where we create the distance offset. Again, as we saw in the first episode, we have a constants class. So here in this case, we have 0.02. And in our case, that's going to be 0.02 meters or 2 centimeters. And that's how your distance sensor works. We're now going to move on to the limit switch, which is oh so complicated. I'm kidding. It's simply limit switch.get. If it is true, the switch is activated. If it's false, the switch is not activated. Same thing with the encoder, but before this looks too easy, I would like to first have us look at this. You can see this is the part that I went past earlier. we have set distance per pulse. Now, there is within your encoder a system, often magnetic, of ticks, right? And you will usually see either 2048 or 4096 ticks per rotation within an encoder, right? And because of that, you might have different ways you want to get your distance, right? Let's say, you know, we had the elevator earlier that we were just talking about for the distance sensor. In some cases, you might not want a direct distance sensor. For example, let's say you have a pulley that's running that elevator, right? You might want to count the rotations of the pulley instead of the distance of the elevator, because that's just what you have on hand. And there's a couple things you'll need to do for that. Let's say you want to measure that in meters, right? Well, you're going to have to first take that, say, 2000, let's say you have 2048 ticks, right? You need to say, okay, so first we have 2048 pulses, so we want one rotation for every 2048 pulses. Then you'll need your circumference, right? If you've never done stoichiometry, you should learn about it because that's exactly what you're doing here. And you're going to use a set of conversion rates, right? And you're going to plug that all into one math equation, and that's what you're going to put in your distance per pulse. Also, you can set reverse direction if you need to. This one's a lot more simple than distance per pulse. But once you have that, you have your distance setting and you have your direction. Now it's very easy to just say get distance, and it will have done all the math for you. And you can get an answer in meters instead of ticks, right? Because nobody knows how much a tick is. All right, so lastly, I would like to show you how to get this information and give you two ways. The first is the bad way, right? A print statement is great for your computer science project, not so great in FRC. You are often trying to read a lot of information. Maybe you're testing and you're trying to, do it very quickly because the mechanical team only gave you 5 minutes to program the entire robot. Or maybe you are on the field and you're trying to get information while you're going. You're the drive coach. You're trying to see how are things going. And in that case, you don't want a million print statements just rolling by. You want an organized way of doing it. And there's a couple ways to do it. Right here I have the Smart Dashboard. I'm also a fan of using Shuffleboard, but in this case we're just using Smart Dashboard because that's kind of the base, and you can really take what you have on Smart Dashboard and use it in other ways. So you can see the first way you would do it is, have your label and then do plus and then have photoelectric sensor and then do a new line and you repeat that. Or you can simply say, right, if you're trying to detect the object, you don't have to take your photoelectric sensor as a number. You can put it as a Boolean and get a true false or a green versus a red, any way you want it to appear. And it'll look nice and it won't be constantly running by such that you're reading it constantly. And what's also nice is you can put down numbers, right? You can have the distance, you can have the limit switch. It's a very organized way of doing it, and it's really the way that you should do it. The only way, or the only reason that you should have for doing system.out.println is if you are just doing like a really quick test and you don't need to see this information a lot. And then after that, you should delete that line because nobody likes seeing lines and lines of text scrolling by. All right, now I want us to try implementing these sensors with something that's actually useful, right? And so I've got this subsystem that we're going to use called photomotor.java. The idea is we're going to have a motor and it's going to spin when a photoelectric sensor detects something, right? So as we saw in the first episode when we made a motor spin, we now have the SparkMax class, right? We have our ID from Constance, and we also have our motor type, which is, again, always K-brushless if we're using the Neos. And we also have that analog input. Again, you'll need to make sure that the sensor is plugged into the analog port of your RoboRio. And again, it will also have its own ID. So there are two ways to do this, right? I'm going to first show you a bad example, and I'm going to show you a bad example because it's really easy to understand. And then I'm going to show you what we do instead. So first you can say, all right, if we detect an object, right, then run the motor, right? Very simple. And then you say, if we do not detect an object, then don't run the motor, set the speed to 0. Very simple, right? And you might be saying, what's wrong with this? And nothing's wrong with this. It's kind of, it'll function in the same way you could write 100 lines of code instead of one for loop. You can do it, but it's not the best way. So let me show you another option, right? So what we use in WPILib is called a trigger, right? And a trigger is very nice because it's woven into the command-based programming that we had talked about a little bit in that first episode, and that we constantly are running commands to a scheduler. And a trigger is just one way of doing that, right? So a trigger is always running, right? And it always exists. And so you can see in this case, we are creating a trigger. We're going to call it photo trigger. And this is just the syntax. Don't get like too freaked out by it. This is just how it's done. And it's going to have this Boolean supplier in it. And a Boolean supplier is basically just a Boolean, except it looks a little funny. The end result is that you have this Boolean value here, right? And it's the same stuff that we're using to detect, except now you can use it in the same way that we were using a button in the last episode. You can use a trigger right here. And in this case, you can see in the constructor, we can now use this trigger and have these rules that on true, we will set the speed to 50%, and on false, we will set the speed to 0%. So when we see an object, we run the motor. When we don't see an object, we don't run the motor. It's very simple. It's the same as the bad code, except in this case, we can use this trigger anywhere, right? If we make this trigger public and we make commands, we can weave in the trigger. This trigger can be used anywhere in the project, right? It's like kind of like a method in object-oriented programming, right? You could write the same code over and over and over again and it would have the same effect, but when you have a method, it just makes it so much easier to program and so much more organized, and that's why we use the trigger. So now you are done. You have created a system that will read a sensor and make a motor spin on top of that. And this might seem like a very weird and arbitrary thing to do, but this is actually very important because this is actually, on a very basic level, the intake system for our 2025 robot, right? It was very simple. We have a ramp and we have an object that goes on that ramp, and we want to detect when that object is there, because when we see an object there, we want to spin the motors for the intake. And then we simply spin those motors until we detect that the object is not in the ramp, because it now must be in the sort of holster that was there to then shoot the object. And yes, so you've now created an FRC component, and now that is the end of the video. So thank you for watching.